Example 4, graph the function f of x, which is equal to the sine of x plus the sine of 2x for when x is in between 0 and pi. And we're going to estimate all the maximum and minimum values, intervals of increase and decrease, and inflection points. So if we graph this on Desmos, okay, so here is our function going from 0 to pi. Okay, so we first note that f is periodic with period 2 pi, and also f is odd, and the absolute value of the function is going to be less than or equal to 1 for all x. So the choice of a viewing rectangle is not a problem for this function. Now we're starting with 0 to pi, and then we're going between negative 1.1 to 1.1. So this is the graph number 1 of the function f of x. Now it appears that there are 3 local maximum values. So let's point them out. So we have 3 local maximum values. There's a local max, there's a local max, and then another local max. So there's your local maximums. Okay, and then there are 2 local minimum values. So here is a local minimum, and there is another local minimum. Okay, now to confirm this and locate them more accurately, we want to be able to calculate the first derivative. So we have f of x, which is equal to the sine of x plus the sine of 2x. So if we want to find the first derivative of this function, then it's going to be the derivative of the cosine. So we're going to take the derivative of the sine, which is cosine of x plus the sine of 2x. And then we're going to multiply it by the derivative of what's inside the parentheses. So it's going to be 1 plus the derivative of 2x is going to be 2, and the derivative of sine is cosine of 2x. So therefore, there is our first derivative. Now what we want to do is we want to graph both the function and the first derivative, and then take a look at the first derivative test. So let's go ahead and do that. So here we graphed in number 2, and let's label this. So here's graph number 2. We know that the red graph represents the derivative of the function, and we know that the blue graph represents the function itself. Okay, and so what we want to do now is we want to be able to then approximate the following values. So we know that there are intervals of increase from 0 to 0.6. So we can see here that from 0 to 0.6, it is increasing. Okay, and where else is it increasing? It's increasing between pi over 3 to pi over 2. So it's increasing here. Okay, so we know it's increasing from here to here. I'm sorry. From pi over 3 to pi over 2. And then we also know it's going to be increasing from 2 pi over 3 to 2.5. So it's increasing here on the second derivative, the first derivative, and so there it's increasing. Now, where is it decreasing? So the levels of decrease are going to go from 0.6 to pi over 3. So from 0.6 to pi over 3, so it's decreasing here. So it's decreasing from here. We also know it's decreasing from pi over 2 to 2 pi over 3. So we know it's decreasing here. And we also know it's decreasing from 2.5 to pi. So from 2.5 to pi, we know that it is decreasing. Okay, so now we want to figure out where are the local maximum values. Well, the local maximum values are located on the function of 0.6 to 1. So here is the local maximum value. We also have a local maximum value at pi over 2 and 1. So there is another local maximum. And then we also have a local maximum of 2.5 and 1. So there is the other local maximum. And then the local minimum values are located at f of pi over 3 to 0.94. So again, there is your local maximum. And 2 pi over 3, f of 2 pi over 3 is 0.94. Okay, so again, we can see here that the first derivative is telling us where the local minimum values are, and here we can see that these represent the local maximum. Okay, so therefore that gives us that information by finding the first derivative. Okay, so now what we want to do is we want to find the second derivative. So we're going to graph the function and the second derivative in graph 3. So let's go ahead and copy down our first derivative. So that was our first derivative, and now we want to be able to find the second derivative. So if we find the second derivative, we know that we want to be able to find the derivative of x plus the sine of 2x. So that means if we take the derivative of x, we get 1. The derivative of sine is going to be cosine. The derivative of 2x is going to be 2. So this is going to be 1 plus 2 times the cosine of 2x. And that is squared. Negative, and then this becomes times the sine of x plus the sine of 2x. And then using the product rule, this is now going to become the derivative of 1 plus 2 times the cosine of x is going to give us negative 4 times the sine of 2x times the cosine of x plus the sine of 2x. Okay, so we're multiplying those together. Okay, so this gives us our second derivative. Now we want to be able to graph the function and the second derivative in the same graph. Okay, so here we have our graph with our function and our second derivative. So let's go ahead and label that. So we know that this is graph number 3, and also our function is in red in this graph, and our second derivative is in blue. So now let's figure out what's happening. Where is it concave up? Well, we can see that it's concave up on what interval? Well, it's concave up between 0.8 and 1.3. So if we look here between 0.8 and 1.3, it's concave up. So it's in between those values on the second derivative. Okay, and it's also concave up between 1.8 and 2.3. So it's concave up here between 1.8 and 2.3. Okay, where is it concave down? Well, it's concave down between 0 and 0.8. So therefore, it's concave down here, and on the second derivative, it's going between 0 and 0.8. It's also concave down between 1.3 and 1.8. So here it's concave down between 1.3 3 and 1.8. And it's also concave down between 2.3 and pi. So there we see that it's concave down between 2.3 and pi. Okay, and now where are the inflection points? Well, we have an inflection point at 0, 0. We also have an inflection point here at 0.8. So on the graph, we can see the point 0.8 and 0.97. Then we have another inflection point at 1.3 and 0.97. So here's 1.3 on the x-axis, and then here is the point 1.3, 0.97 on the function. And then we have another inflection point at 1.8, 0.97. So here is 1.8 on the x-axis, and then on the function here is the inflection point. And then at 2.3 and 0.97, again here is the value of the x, 2.345, and there is the inflection point on the graph of the function. Okay, so now to conclude here, having checked that graph 1, which is the first one, indeed represents f accurately between 0 and pi, we can state that the extended graph here in graph number 4 and that is of the function represents f accurately where x is in between negative 2 pi and positive 2 pi.